All right, so in this video, we're going to be looking at three non-parametric regression methods: smoothing splines, LOESS models, and Gaussian processes. So we're going to start with pulling in our data, which we're going to use the MT-CARS data set for. And we're going to pull in our ggplot. And then we're going to start by plotting our data. And just make a scatter plot to start with. And we're going to start with the displacement, and we're going to use that to predict MCG. And so here we have a graph of our data. Now, as we've seen in previous analyses, this data is clearly nonlinear. And so there are different ways that we can try to work with this data. We could try, as we've done in a prior video, we could try to do transformations of this data. We could do log, for instance, of either MPG or displacement to try to model the data that way. We could do other kinds of transformations, square roots, some combination of transformations, use nonlinear models such as including squares or other kinds of components. But in all of those cases, we have to make decisions about what kind of nonlinearity we're dealing with. And so dealing with non-parametric regression methods might allow us to model the data without having to make those decisions in advance. So we're going to start with smoothing splines, and we're going to pull in another library. And again, if you've never used this package before, make sure that you download it from the tools menu and install it first. And then we're going to build a smoothing splines model. Now, there are many kind of spline models that are out there. This is just one example, just to kind of get our feet wet. But certainly investigating other kinds of packages that can do splines are worth looking into if you're interested in doing more nonlinear modeling like this. Now, in spline models, the knots are essentially the number of places where we're breaking up our data set into chunks. And then we're going to essentially model pieces of it and try to knit them back together again. Smoothing splines, by definition, suggests that we're trying to do it in a smooth way. But essentially, we're going to break the data set up into pieces. So this would have to be some sort of an integer. I've seen some examples with as few as 3 knots, but you can certainly experiment with the number of knots. 5 is kind of typical. And then we can print out the result. Again, it's going to remind us of the call. We have degrees of freedom. So again, you can kind of think of that as a parameter that we can adjust by making various adjustments to our data set. Penalized regression criterion, the RSS, the lambda that gets used in, again, doing the smoothing function. We can also use another kind of function called a smoothing spline, SMSP. Smooth dot spline. Again, we're using 5 as the number of knots. Again, check the documentation for what other kinds of attributes that you can modify. And again, we get some information about our model. Equivalent degrees of freedom here is 5.6 instead of 5.7. So this is the penalized regression criterion is 108 as opposed to 109. The parameters tend to be a little bit different from these two functions. You can see they're still kind of in the same ballpark. Now, if we want to plot these two models on our graph to see how they do, we can do that. This is in base R plotting. So this would be our smoothing spline curve. You can see it's non-linear. It's not a smooth, like log type expression. It's not a straight line. It's not a quadratic. But it's, again, it's basically taking this graph and chunking it up into pieces and then trying to model those components and then still manage to fit the pieces together. If we look at our second model, then you can see it's actually quite similar. The function produces a slightly different outcome. We see that in this middle section, it's a little higher. The new one is a little lower. It kind of goes through this a little bit more smoothly. The curves at the knots are not quite as sharp. And then we can add a legend to the graph. And so we've added our legend in order to explain. And again, you can add other things like a title by adding a main to the original plot and so forth. You can also, with the SS function, you can also plot error bars relatively easily. So again, this is without the points on it, but you can see that it's plotting the error bars and they're not consistently thick everywhere. So that is a feature of the smoothing splines function. You can also get some summary data. And again, the proximate significance of non-parametric effects. You can see whether it's relevant to keeping in the data, how good the equivalent R squared value is. So you can compare your results to other results, other kinds of models that you might be using. Now we can adjust the parameters of the smoothing spline to adjust the results. So there is a parameter lambda that essentially adjusts the smoothing component. A value closer to 0, there will be less smoothing. The graph will be jumpier and have more sharp curves. If you adjust the value upwards, set it larger, then that will smooth it out. But if you set it to too large value, then it will tend to become more linear. So let's look at how we can adjust that. And I'm going to start with something pretty small. And then we're going to plot this. And we're adding the points on after the smoothing curve. Now, if I want to adjust the lambda, I could make it smaller, for example. I could make it larger. Oops, that's why that didn't work. Let's try that again. I thought that looked the same. My own fault. So a much smaller lambda, you can see you get a lot more jumpy behavior. You can set it a little larger. Maybe set it something like that. And already when you set it equal, again, it's about 3 times bigger, it's already extremely smooth. It's still not quite linear, but it clearly is trending toward linear. And you can certainly make it like 1. And you can see that it's basically a straight line at this point. Again, as you make these adjustments, you might want it to be quite chaotic and messy. Or again, you might prefer something sort of in between these two values. When you are doing your models, again, sometimes this is going to depend on the number of variables. Sometimes this is going to depend on the number of components that you have, the number of observations. So you may need to experiment with some of these. We can also adjust the value of m. And so we'll go back to our original lambda value. Again, we can see that it's a little bit jaggedier. And 2 was a little smoother. If we make this 3, then again, still curvy, but it's smoother than it was at the same value of lambda, but with m equals 2. So these are various parameters that you can play around with. There are certainly other packages that can do splines, such as splines 2. And again, make sure that you load this, install it under tools before you run this. Now, what's happening here is we're actually creating new displacement observations that we can then use to predict the line. So I'm calculating the minimum of the original variable, the maximum of the original variable, and then calculating an increment size that essentially will give me a sequential list of displacement values that I can use to plot the curve. And make predictions. Now, in this case, we use the B-spline with a degree of 1, which is why this looks very sort of chunky linear. You can certainly update this degree to have other degrees, so like degree 2 or degree 3, for instance, in order to get a smoother function. So, for instance, so just by increasing the degrees and the degrees of freedom, we have a much smoother function, and we can then plot the displacement against the MPG on the same graph. So again, for your particular model, you will want to experiment with some of these parameters until you get your best fit. Doing things like extracting the residuals and things like that in order to assess how good your model fit is. And again, see the documentation for these packages in order to see what other kinds of parameters you can adjust and other things that you can extract from the models. Now, the second type of model that we're going to look at are LOESS models. And the idea behind a LOESS model, there's a couple of different ways that you can perform a LOESS model, but typically it's some sort of piecewise polynomial process where you fit a sort of low degree polynomial, typically degree 2, although you can use straight lines as well. But a low degree polynomial for just a subset of the data. So maybe 50% of the data or 75% of the data. The larger the chunk of the data, the more like the traditional polynomial it will be. the smaller the chunk of the data, the more variability you can get, the more kinds of turning points and things like that that you can get to model specific chunks of the data as various aspects of it change. Default values for the LOESS model tend to be in the range of 2/3 to 3/4, depending on the specific function that you're working with. But we can always specify those particular components with the span attribute. So again, we're going to model MPG with displacement. And for some of our examples, we're going to start by setting the span to around 0.5. Now, one cautionary thing about the span, if you have a lot of data, you can go quite low in terms of the percentage of values that are included in your model. However, if you don't have a lot of data, your span can't be lower than the like 3 or 4 components. If you want to get 4 components, if you want to get any error measurement at all. So there is sort of a lower bound on this span value that you can get for small data sets. Again, it will be very small if you have a very large amount of data, but it can be quite large depending on if you have a very small data set. I'm looking at the wrong line. So we'll look at 3 examples. We'll look at a span of 50%. We'll look at a span of 75%. And then we'll also look at a 90% case. And now let's all plot them on the same graph. So you can see, again, if you use like the blue, you have 90% of the data, you get a much smoother curve with much fewer twists. 75% is the purple line. So you see some deviations, particularly in the middle of the data set, from what the 90% line is doing. And then the red line you can see is much more flexible. It's using much less of the data. And so it is a little bit more wobbly, shall we say. It's not quite as chaotic as we saw with one of our lambda values. like this one, it's not quite there. You could try to take the percentage down a little bit further and a little bit further. Again, depending on how much data you have, you may be able to achieve this level of, shall we say, chaos. Um, but generally, you'll get smooth functions. It's just more variable or more smooth depending on the degree, the span that you choose for your models. And then we can also get summaries of our models. So let's just compare two of them. In this case, we have, again, it gives us the call. The number of observations is 32. The equivalent number of parameters is 6.33. So if we were to think of this as replacing it with a polynomial model, this is suggesting we would need essentially a degree 6 polynomial to get this kind of behavior. It gives us the residual standard error and some other information. It's assuming a Gaussian error family and so forth. Now, if we were to do the same thing for, let's say, 75% span, then our equivalent number of parameters is now down to about 4. This would be like a quartic polynomial, more or less. Residual standard error, that's 2.295. Here it was 2.184. Again, there's always a danger in overfitting if you make your span too small, just as there is a danger in overfitting if you make the degree of your polynomial too large. So you do have to take things like that into account. Now, LOESS is a nice function because that is the default function used for smoothing plots in ggplot. So it does make plotting them in ggplot very straightforward. Put points on there, and then geom smooth. And when we plot it with ggplot, we can also get the error bars plotted very nicely. You can also put in properties like the span, and it will adjust the span. Again, there's a default value, which I believe is around 2/3 to 3/4, but you can reconstruct your 50% plot by just adding span equals 50%. And again, you can see that it's a little bit more wiggly. Now, if we wanted to plot the spline model and the LOESS model on the same graph, we can do that, and we'll look at an example in base R. Well, our examples here have only one independent variable plotted. There are packages in R that can do at least two independent variables for both of these splines and LOESS functions. Now, the last type of non-parametric model we're going to consider are Gaussian processes. And Gaussian processes, there's so many packages, there's at least half a dozen of them that can do Gaussian processes, and they all work a little bit differently. But we're going to use the library Robust Gath. And again, install it from the tools menu before you run it. Now, this one does require that we convert everything to a matrix in a similar way that we had to for penalized regression. And the other thing that we have to do for this particular package is that it likes things rescaled, typically between 0 and 1. There is an exponential function involved in the model, and so having very large values tends to produce wonky results. At least for the input variables. And so here's our mean parameters, our variance parameter, our range parameter, and our noise parameter from our model. And then we can also plot the result. If you get warning messages, as long as they're warnings and not errors, then you can mostly ignore those. So we're going to plot our result. And again, we have to construct some input values so that we can do that. There we go. So this is our Gaussian process regression. Now, if we wanted to plot it on the original range of values, we could do that after we created the model. We would then simply have to scale back our adjustments that we made to the input variables. So we would have to take our test input after we modeled it, multiply everything by 500, and then same thing with our input, multiply everything by 500, and we could get it back on the original scale. But for just the example purposes, I'm not going to worry about that. And then if we want to compare all three models on the same graph, we can also do that as a final act of comparing everything. Or if we could just rescale everything downward so that they're all on the same model range as the Gaussian process. And then we can take our Gaussian process models. Again, we're not changing anything in terms of that component. And then we're going to add in our LOESS model. Again, I'm dividing by 500 to put it on the same scale as the data we have here. Now, one thing that you may notice about this data is that the Gaussian process model, you can actually extend beyond the range of the original data. If you try to do that for the LOESS model, it will not work. It will yell at you. Now, I don't really know off the top of my head whether it will do it for the spline model. Some may do it, some may not do it. But when you extend past the initial input variables for the LOESS model, the LOESS for the Gaussian process model, the model outside the range of the data will tend to go toward the mean of the overall data rather than going off like a polynomial might off to infinity. But I have tried at least to extend the LOESS model outside the range of the original data, and it definitely doesn't like doing that. So if you need to extrapolate, the LOESS model won't really do that for you, but the Gaussian process model will. And again, in a predictable way, not necessarily the way that you want it to, but you can also modify this model to provide trends that continue outside the range of the data. So you could impose, for instance, a linear trend outside the data that you have other than just the mean. So it is a very flexible model.